Today we're exploring 3 lesser known yet utterly fascinating thought experiments that are going to twist your brain in knots. First, we'll tackle quantum suicide, a mind-bending scenario that changes the very foundations of reality and our understanding of life and death. Next, Newcomb's paradox, where free will clashes with predictive entity. And finally, the Sleeping Beauty problem, a philosophical puzzle that will make you question how probability and belief intersect. You've probably heard of the Schrodinger's cat thought experiment, but we'll give you a quick refresher. A cat is placed in a box with a vial of poison, an atom of radioactive material, and a Geiger counter. After one half-life of the atom, there is a 50% chance that the atom will decay, triggering the Geiger counter, which will then release the poison. At this point, the cat now has a 50% chance of being alive, but thanks to quantum superposition, the entire system can remain in both states until observed. Under the Copenhagen interpretation, this is precisely what happens. The cat is simultaneously both alive and dead, and the system doesn't collapse to a singular outcome until the evil scientist performing the experiment opens the box to observe the result. At that point, the cat will only be alive or dead. One of the numerous potential issues with this view is that because the cat was both dead and alive, it should have a memory of being dead. While this has never been tested experimentally, and with good reason, we have no reason to believe that a cat in this scenario would have memories of its time being dead before the box was opened. There are also other questions regarding whether it's even possible for such a macroscopic system to exist in a quantum superposition, all of which challenges the Copenhagen interpretation. The more popular solution is the many worlds interpretation. Under this framework, the system results in 2 parallel universes, one where the cat is dead and one where the cat is alive. Opening the box doesn't collapse the possible outcomes, it merely reveals which timeline the observer is part of. There should be 2 alternative realities with copies of the same scientist each observing a different result. But those 2 scientists have no ability to communicate with each other, meaning that the end result observed is no different than the Copenhagen interpretation. There is a single cat that is either dead or alive. So, if these wildly different interpretations of quantum superposition both would have the same experimental results, how can we possibly design a test to support one theory over the other? And that's where the idea of quantum suicide and quantum immortality come into play. Though several others presented similar ideas in the preceding years, this thought experiment is usually attributed to the Swedish-American physicist Max Tegmark and his 1998 paper. This experiment is a hypothetical means to test the many worlds interpretation, and for once, it doesn't involve the senseless murdering of cats. Instead, it is the scientist himself that gets to get into Schrodinger's box. Rather than a vial of poison, the box will have some sort of murder machine that instantly kills the scientist before they can even feel anything. Once a radioactive atom decays, their death will also happen faster than they can read the Geiger counter or any other measurement tools. These modifications are designed to remove the argument that the scientist would count as an observer of the system, as they would have died before any observation could occur. More importantly, however, instead of a single radioactive atom, the box will contain hundreds. Each atom has a 50% chance of decaying over the course of one half-life, so according to the many worlds interpretation, each of these will result in the creation of a parallel universe, one where the scientist dies and one where they don't. But because there are hundreds of atoms, the overall odds for the survival of the scientist are the same as flipping heads on a coin hundreds of times in a row. It's essentially 0. Do you ever feel that your online life is a bit of an open book? Well, fear not, because I've got something that will change the way you use the internet. Picture this: you're planning your next big getaway, but your online privacy is like a leaky faucet. Credit card numbers, addresses, all of that stuff. You don't want that leaking, and that's where Surfshark comes in, the ultimate solution to digital privacy problems. Surfshark isn't just a VPN, it's your online guardian angel. Surfshark will mask your online activity with top-grade encryption. Plus, it's incredibly easy to use. Even your grandma could do it. Simply connect, and you are done. Your virtual location is wherever you want it to be, and it's private. Whether you're sipping coffee at a cafe or scoring a good deal online, Surfshark keeps you secure. Plus, they've got you covered with Surfshark Alert, antivirus, and search add-ons. It's like having a digital superhero for your internet. The best part, one subscription, unlimited devices. Share the love and keep everyone safe. Plus, if you use the promo code Sideprojects, you get 3 months for free at surfshark.deal/sideprojects. 3 months on the house. Stay secure, stay private with Surfshark. Thank you to them for sponsoring. And now back to today's video. From the scientist's point of view, however, the odds of survival under the many worlds interpretation would be 100%. So how can that be possible? The first atom has a chance to decay, at which point it creates 2 parallel universes. If we ignore the possibility of an afterlife, the scientist's consciousness will never exist in the universe where they die, only continuing in the other universe where they survived. That's where the paradoxical nature of this experiment comes into at play. Winning all of these coin flips in a row may be a near statistical impossibility, but under the many worlds interpretation, it is a necessity that all outcomes exist. As such, the scientist's consciousness will only travel along the singular path of potential outcomes in which they survive the entire ordeal. Despite their death under the conditions of the experiments being all but certain, quantum physics would demand that they survive, making the person functionally immortal. At least immortal in regards to this particular experiment. They will absolutely still die eventually. While quantum immortality seems like an elegant way to prove the many worlds interpretation is true, there are a couple of problems. First, it would require creating an absolutely mind-blowing number of alternate universes in which the scientist died, and the theory would only be proven true in the one where they survived. And because the odds of survival are effectively zero, their claims of success are likely to be dismissed and chalked up to the death machine not working properly anyway. As frustrating as it would be to prove the many worlds interpretation and have nobody believe you, fortunately, that should never happen. No scientist would actually be stupid enough to turn this thought experiment into an actual experiment. Would you like some free money? Well then, American physicist William Newcomb has the thought experiment for you. Newcomb devised his thought experiment around 1960, and he discussed it frequently with fellow physicists and philosophers. It was first published by American philosopher Robert Nozick in 1969, and people were already extremely divided. Nozick noted in a follow-up paper in 1969, quote, "To almost everyone, it is perfectly clear and obvious what should be done. The difficulty is that these people seem to divide almost evenly on the problem, with large numbers thinking that the opposing half is just being silly." So, what exactly is the confounding problem? Well, Newcomb's paradox is a very simple game. You're presented with two boxes. One's labeled A, one's labeled B. Box A is clear, and you can see that it contains $1,000. Box B is opaque, and it will contain either $0 or $1 million. You must choose whether you want to take the mystery box or if you would rather take both boxes. The twist is that a reliable predictor has been determined beforehand which you would choose. There are variations on this where the prediction is 100% perfect, but those get into arguments about free will and reverse causality and a bunch of other stuff that really is beside the point. For our purposes, we'll assume that the predictions are correct 90% of the time. They are usually correct, but the predictor is fallible. Anyway, if it predicted that you would only take box B, then that box will have $1 million inside it. If it predicted that you will take both boxes, then box B will be empty. The prediction was made before you were presented with the boxes, and the contents of box B have already been finalized. So, is the correct answer to only take box B, or is it to take both boxes? When presented with this question, most people immediately assume there is one answer that is obviously correct. You're probably already sure what the optimal strategy is right now because the setup for this question is so simple. But, as Nozick alluded to back in 1969, half of you watching this video right now think the correct answer is obviously to only take box B, and the other half think the obvious answer is to take both boxes. You must take both boxes. Why would you take one? By the time you get to choose the box, the contents of box B are already fixed. If the predictor chose you would only take the mystery box, and you take both, you will get $1,001,000 instead of just $1 million. If it predicted you would take both boxes, then by taking both, you would get $1,000 instead of nothing. In game theory, this is called the strategic dominance principle, because one course of action always has a better result than the other, regardless of what the other player chose. So, it's settled then. You should always choose to take both boxes. Right? Well, not necessarily, because that decision would have been predicted with 90% accuracy. This means that 10% of the time the prediction will have been wrong, and you will get $1,001,000, but the other 90% of the time you'll only get $1,000. Oh, I see. Whoa! That means that the average value of taking both boxes is only $101,000. However, if you only take box B, 90% of the time you'll get the $1 million, while only 10% of the time you'll get nothing. That means that the average value of choosing only box B is $900,000. In game theory, this is called the expected utility principle, and it is just as valid as strategic dominance. That is the source of the paradox, as two equally flawless forms of analysis result in contradictory answers. This is amazing! Have I never heard of this before? And while one of these answers may have initially seemed more obvious to you, neither is particularly more obvious than the other as a general rule. Decades of countless surveys have shown that people are consistently split nearly 50-50 on this question, with the decision to take both boxes usually being a couple of percentage points more popular. These numbers remain consistent even when the survey only includes professional philosophers, mathematicians, and game theorists, so it's not like there really is some complicated yet definitive decision matrix that can solve this problem. In 2011, a well-received paper by physicists David Wolpert and Gregory Benford claimed to have unequivocally resolved Newcomb's paradox and stated that there was only one correct solution. So, which answer did Wolpert and Benford choose? Well, rather frustratingly, they chose both. According to their paper, the nature of how the prediction is made is a bit vague, and as such, there are two completely different games being played, depending on how you assume the probabilistic nature of the predictor's decision works. The two possible choices are each correct in one version of the game, but not the other, and everybody just chooses whichever option is correct for the version of the game that they believe is being played. Unfortunately, Wolpert and Benford did not weigh in on what they believed was the correct interpretation, leaving us no closer to a definitive answer. However, they did make some interesting word choices that you're free to interpret however you like. They defined taking both boxes as the realist position and only taking box B as the fearful position, arguing that the latter position was seemingly based on the participant believing that they lacked free will in this scenario. That's wild. That's totally wild. The Sleeping Beauty problem was first published in 2000 by philosopher Adam Elgar, expanding on ideas first introduced in 1990 by philosopher Arnold Zuboff. The setup for this thought experiment is very simple, but agreeing on a solution has proven to be much harder. Our test subject for this experiment is Sleeping Beauty, who has been made fully aware of the details of the experiment beforehand. On Sunday, Sleeping Beauty will be put to sleep. While she is asleep, one of the researchers will flip a fair coin. If the coin lands on tails, she will be woken up on Monday and asked a single question as laid out by Elgar. What is your credence now for the proposition that the coin landed heads? In this context, credence means what does she believe is the probability that the coin landed heads. After answering the question, Sleeping Beauty will be given a drug that will make her fall back to sleep and forget that the interview ever happened. Then she will be woken up again on Tuesday, asked the same question, and put back to sleep. If the coin landed on heads, she'll only be interviewed on Monday and will sleep through all of Tuesday. So how should Sleeping Beauty answer the question when she is interviewed? There are two conflicting schools of thoughts here, both of which have proofs that are accepted as being mathematically valid. The first answer is the third position, which states that Sleeping Beauty should believe that there is a 1/3 chance that the coin landed on heads. This seems counterintuitive, since by definition a fair coin has a 50% chance of landing on heads, but the math behind this argument is actually sound. First, let's assume today is Monday. When Sleeping Beauty is woken up, the probability of it being Monday and tails is equal to the probability of it being Monday and heads. Next, let's assume that the coin lands on tails. Since a tails always results in her being woken up twice, when she is woken up, the probability of it being Monday and tails is equal to the probability of it being Tuesday and tails. Since the probability of Monday tails is equal to both Monday heads and Tuesday tails, all three outcomes have the same probability. Now, some of you might be screaming at your computer right now that this sounds like some sort of trick, but we promise you that these two equalities can be combined like this even though they were derived from different assumptions. You can even test it yourself by flipping a coin 100 times and keeping track of when Sleeping Beauty will be woken up. Assuming fair coin flips, you will find that she is woken up at each of the three possible timings about 50 times each. Because all three of these events have an equal probability of happening, thirders argue that Sleeping Beauty should say she believes there is a 1/3 probability that the coin landed heads. After all, 2/3 of the time that she is interviewed, it is because the coin landed tails. This was the position that Elgar took, and while there is no general consensus, it is definitely the more popular of the two answers among philosophers. However, it happens to be the rather vehement opinion of the writer of this episode that the third position is an utter abomination, and all of those who support it should be ashamed of themselves. Kevin wrote this, and I'm curious as to why, because I like it. The half position argued that Sleeping Beauty should believe that there was a 1/2 chance that the coin landed heads because there was. By the very definition of it being a fair coin flip, the odds were 50%. Sleeping Beauty went to sleep knowing this, and when the researcher wakes her up, she has no new information. She has no idea what day of the week it is, or if she has already been interviewed. Since she knew that it was a fair coin flip, why should she suddenly believe there is anything other than a 50% chance of the coin landing on heads? It's counterintuitive, but the math says so, Kevin. Instead of flipping the coin while Sleeping Beauty was asleep, the researchers could flip it on Sunday while she was awake and ask her what she believed the probability was that the coin landed on heads. And of course, she would say it was a half. Likewise, when the experiment ended on Wednesday, if she was again asked the question, now knowing that the experiment had ended, she would always answer that it was a 1/2 probability that the coin landed on tails at the beginning of the experiment. Thirders try to make the answer seem more persuasive by extending the length of the experiment to better illustrate their point, such as making tails result in Sleeping Beauty being woken up and mind-wiped 999 times. By extending the equalities we did earlier, this could prove there is only a 1 in 1,000 chance that the fair coin landed on heads. However, these events aren't independent of each other. Either all 999 tail events happen or 0 of them do, and that is a 50% chance. Of course, the real issue may be that the question itself is ambiguous and that thirders are answering a question that wasn't asked. The question posed by Elga in the original paper, and the question that is always asked of Sleeping Beauty, is what do you believe is the probability that the coin landed on heads? She knew it was half when she went to sleep and had no new information when she woke up, so of course the answer to that question should remain unchanged. However, if the question being asked was, what do you believe is the probability that I woke you up because the coin landed on heads? Well, that's a completely different situation. If the coin landed heads, she will be woken up once, and if it landed tails, then she would be woken up twice. So, of course, tails is the more likely option under this phrasing. The experiment was repeatedly performed, and Sleeping Beauty was going to be given $100 every time she correctly guessed whether the coin landed on heads or tails. She would make twice as much money by always guessing tails. Not because tails was a more likely result, just because she was asked more times, and it was the correct answer. To many people, that may sound like an endorsement of the third position, as this sort of wager argument is often used to illustrate their point. However, here's one final variation of this thought experiment that may help show the difference between the question being asked and the question that thirders seem to be answering. So let's stop injecting Sleeping Beauty with drugs, and instead we'll use a simple ball pit. Whenever a fair coin lands on heads, 1 green ball will be put in the pit, and whenever it lands on tails, 2 red balls will be put in the pit. We could flip the coin 1,000,000 times and ask you what the probability is that a green ball was put in the pit, and every time you'd correctly say that it was half. However, if we were to then pull 1 ball at random out of the pit and ask you what the probability is that a green ball was removed, well, the answer may now be 1/3, but it's a very different question.